the opportunity to very nice workshop. As always, it's a pleasure to be at the Simon Center. So, what I will discuss is part of some joint projects in progress with Fabian Hayden, Maxim Kuntsevich, also with Georgy Dimitrov. And with so it's my humble attempt to understand the work of several works of Gayotto, Naetsky, and Moore. So, of course, that's really a rather difficult task, taking into account my mathematical limitations, but some wise guys joined, and I don't mean the New Jersey or New York meaning of the word, although on second thought might be the same. So the plan that I will follow is first give you a motivation, then I'll give some definitions and examples, then I'll talk about some applications, and I'll probably have time to only discuss one or two of these correspondences. So let me start with some brief reminders of some classical well-known results. So if I have a Riemann surface, I choose a point on it. So they are well known. In fact, they are dense set of geodesics passing through this fixed point P, meaning closed geodesics. And also we study the Riemann surfaces altogether by considering the Teichmüller space, to which an important feature is the so-called compactification given by Thurston. And so this compactification is by adding certain trees at infinity. And we also have the action of the pseudo-Anosov transformations acting by fixing two of the laminations associated with these trees, which on its own correspond to quadratic differentials. And so now the Teichmüller space is contained in a bigger modular space, and so that is so-called modular space of Higgs bundles. So these are pairs of rank 2 bundle on a Riemann surface C, and an endomorphism so under certain stability condition, that is a nice modular space, which has the following map to H0 of C, kc square. So this is so-called Hitchin map, and this is the base of well understood Hitchin system. And in this particular case, when we have rank 2 SO2 bundles over Riemann surface, we know that this Teichmüller space embeds into this modular space of Higgs bundles as a section of this vibration of the Higgs bundles over the quadratic differentials. And moreover, if you look at this base of the quadratic differentials, and you take a curve on it, so you can consider a representation of the fundamental group into the field of functions of this curve, and that representation produces for us a nice harmonic map, rho equivariant, from the universal coloring of this Riemann surface into the tree associated with this group with no Archimedean field. And so this is a harmonic map. And this tree that we get here is very much related to the trees which Thurston used in order to compactify the modular space of complex structure, the Teichmüller space. So what I would like to do now is to look at this rather well-known picture from the perspective of category theory, or more precisely from the perspective of stability conditions. And let me briefly introduce a couple of definitions. I'll be rather vague here. So let's say that we consider C a triangulated category. Z graded. And so a stability condition on C is a pair of bounded T structure and a heart of this structure, and an additive homomorphism Z from K0 of this category to C, such that we have the following properties. The first is Z of E is equal to Sorry. And the second condition is that for every E in the hard alpha, there exists Harder-Simhan filtration with respect to phi. So this definition introduced by Bridgeland. Of course, physicists have better way of thinking about this. Feel free to use the definition that is well known from physics. It's the same modular space. And immediately another definition. So we say that category C has property D if there exists a stability condition Z such that E in power pi phi forms a dense set in a segment when E runs over all stable with respect to the objects. So in other words, I'll put we have the following picture. So if we go back to this classical picture of one-dimensional dynamical systems, what I would like to indicate is, with these definitions, the role of the Riemann surface and all the structure associated with it is going to be played by some category, in this particular case, well-known Fukaya category of a Riemann surface. So the stable objects are, in this case, just the geodesics. The density of this geodesic passing through a point is just the property D, which I have just formulated. And then we have these compactifications. So these compactifications are going to be for us the stability conditions. And most of the talk will be about the analog of these pseudo-Anosov transformations. So let me just give you some examples well known in physics where I'll try to demonstrate this correspondence. Oops, that's the wrong one. So we don't care too much about the Higgs modular space at the moment. We care only about the base of the Hitchin system. And so, as I have indicated during this using this coloring, these are going to be for us the analog of the stability conditions. If we want to forget, of course, the discriminant loci, which also correspond to stability conditions, but of other categories. So let's do the following table, just to save time. So category stability conditions stable objects property D and differential equations. So we start with a rather simple category, the category N associated with the following quiver, or this is the Mecca of Fukaya categories. You can think of this as a Fukaya-Seidel category associated with a polynomial P of degree n plus 1. So the objects here are either the representations or can be seen as some timbals associated with the covering given by this polynomial. So the stability conditions of this category, as proven by Haydn, Kuntsevich, and myself, look as follows. So in other words, they are differentials given in the following form, where Q is a polynomial of degree n plus 1. So the stable objects are things which correspond to the geodesics, but in this particular case, they are going to be given by just sides and diagonals of the polygon given by the roots of this polynomial. So property D does not hold here. Namely, there is no dense segment. And I'll return to differential equations a bit later. So the next category, which is an obvious generalization of this, is so-called one-dimensional Fukaya-Seidel category. And so this category is basically defined as over a Riemann surface C with some points on it, or without them, and a function from C to C. So in other words, this is just a covering, and the corresponding timbals are just some configuration of points. So in this particular case, as proven by Haydn and Kuntsevich, so we have that the corresponding stability conditions look like as Z in power QZ square. And the stable objects were known a long time ago, if you go back to Gelfand and Ponomarev. So they are so-called bands and strings. This is a very bad translation from Russian. Bands are just these intervals which connect points, and strings are, sorry, these are the strings, and the circles on this Riemann surface, namely the loops, are the bands. So the intervals in geodesics, close ones. So the property D doesn't hold. So this is all happening on the Riemann surface. So these are on the, so Riemann surface has some points, the ones that I have mentioned here. And so on this Riemann surface, I have geodesics or things which connect the points which I have taken away.
So is the Riemann surface, are you taking, removing the points from the Riemann surface and then taking the a function which is
okay. To remove any confusion, a different definition. Let me just take a Lagrangian skeleton on this Riemann surface. And then consider A1 constructible sheaf of categories over generic point. So something is happening at this point. So if you take the sections of this constructible sheaf and perturb a little bit, this is the category that you want to consider.
Can the function f be 0?
You will get the Fukaya category, no. No for this consideration. So now that I see ND arrived, I need to give another example. Just in your own. So the category that we want to consider is so-called AN tilde. A different way to talk about it is to take the following conic bundle. So here, this curve belongs to C2. I'm sorry, these are coordinates in C2, and U and V are coordinates in C star square. A different way to talk about it would be to take a Lagrangian skeleton and put A2 categories generically, and then see what's happened further. So the stability conditions in this case are going to be H0 of CK square, namely an open setting here. So the stable objects, let's actually consider even more general case. The stable objects are going to be the.
Are you considering the compact category of that?
No, I want to take some points out of this Riemann surface. That's what I want. So this Riemann surface, this hyperelliptic curve. So I'm going to take some points out of it. So, and then the corresponding stable objects are going to be this intervals, or if you like, these lines which connect the zeros of the quadratic differential. So this category actually does have the property D, which seem to play an important role in the way the BPS states behave. So in fact, as proven by Dimitrov, Hayden, and Kuntsevich. So as soon as you have a category with exceptional collection, and it contains in itself Kronecker quiver, you will always have this property D satisfied. And so the differential equation that I want to mention here is Schrodinger equation. And by this, I mean that if you do WKB approximation, then of the solutions of the Schrodinger equation over this Riemann surface, what you can actually show that the stable objects that you obtain here have a lot to do with this WKB approximation. And in fact, this procedure and the differential equation itself pretty much determine this category. So in a similar way, if you change this to AN, geometrically that means that you consider the Fukaya category of the total space of C square mod Z n plus 1 over a Riemann surface, construction which was introduced by Dunagi, Pantev, and Diaconescu. Then the corresponding stability conditions are going to be just the base of the Hitchin system. So property D is going to hold. And the equation is just the Lux pair for the Hitchin system. So let me just finish this table by adding an unusual equation here. So in this particular case, which we have started with, the equation that determines the category is some strange modification of Schrodinger, which I wasn't able to trace into physics literature. So this pretty much determines the category. In a way, AN is a limit of the AN tilde case, and that's why we have here this exponent appearing. But so this is just there are many details which I'm leaving out. So in particular, I didn't talk that the stable objects in this case are described by so-called spectral networks, and these spectral networks can be actually lived from the corresponding tree, or in higher rank case from the corresponding buildings. And so in such a way you get a nice combinatorial description of these objects as I have mentioned before. But yes?
So the Douglas scale of the Riemann stability condition given by the central charge varies over the moduli space. Mm-hmm. So the statement, the property D would be moduli space dependent. So a category can have
So, but that's correct. So, but I mean, if there exists a chamber over which this happens, obviously you can always find a chamber where we have only two things. But if you have a chamber, one chamber where you have this thing, then I call the category having property D.
But are you using that stability condition, or are you choosing some?
No, if there exists a stability condition for which this happens, then we say that
so it's not necessarily the central charge.
Yeah, but I don't know of any other. So, all right. So now what I want to talk about is just the analogy with this pseudo-anosovs. Yeah.
Sorry, maybe I missed or didn't catch the words when you drew this picture. Are you saying that the category is a global section of the Schiffer category?
Yeah, perturb. You take the global sections and you perturb a little bit.
And so locally on a smooth point, it's AN?
Yeah.
Do you have a local model for what happens at the vertex?
Yeah, so Oops, sorry. And so I can give you even more. So there's a certain Fukaya-Seidel type of category associated with this point, but let me give you this in private discussion. So I forgot to say this is certainly based on work of Nadler, Zaslov, and company. All right, so now what I want to talk about is just this analogy with the pseudo-Anosov transformations. So again, we restrict ourselves to a category with a generator G, which means that G generates C by means of direct sums, summands shifts and triangles. So now I introduce the following notion. So complexity of the object E2 with respect to the object E1. So this is a function defined in the following way. I take the infimum of the following functions, where ni's are obtained in the following way. So I consider all possible ways in which I can, generate E2 as extensions, or if you like triangles, by shifts of E1. So in other words, I use E1 as a generator, and then I obtain E2 as a summand in some extensions of E1. And then I go over all these possible extensions. I get this infimum of this function. And so this notion is going to be called complexity of the object E2 with respect to E1. So now using this complexity, so we defined, so let me just mention some properties, sorry. So this function has the following property. First, the triangle inequality. In other words, we have the following equality. That's a sum. That's a product here. Yeah. It could be infinite. So in fact, I'll remark on that. So the second property is a retraction map. here. It's a product. Yeah. So retraction map. So if F is a endomorphism, in the category, we have the following inequality. And in fact, so the remark that I want to make is that this is finite if and only if E2 belongs to what is generated by E1. So now, theorem. So let's actually first introduce definition. So again, F is an endofunctor. Acting on C. Then we introduce the function of entropy of F. So G is a generator, as defined up there. So theorem. HT, this is well defined, and it does not depend on the choice of G. So it doesn't matter which generator do I put there, I'll get the same function. So let's try to give an idea of proof of this theorem. So it is based on this triangle inequality. So basically, you just need to show that this is a semi-additive function. In other words, delta T of which easily follows from applying the retraction map and triangle inequality properties. And then with a little bit of calculus, you can show that this actually converges. And in a similar way, you can show that it doesn't depend on G. So now, this seems a function that is hard to compute. But in good cases, namely when the category is mutant proper, then you have the following theorem. The entropy of F can actually be computed in the following way. So it's e in power minus kt. So let's give an example. So let's do something simple. So let's say that this is dB of a point, and the functor is just tensoring with vector space. So clearly, if you apply this formula to this category, so the only x that you are going to have here is x0. So you have dimension of d in power n as a result of the x, and so k is equal to 0. So you have log of this so is of course is equal to log of L. So that is the entropy of this functor in this case. Okay, so a couple of properties, sorry, a couple of examples. So first, the shift functor. So then, let's say shift by n. So then we have ht of n is equal to nt. So the second obvious property is that ht of fn is equal to n times ht of f. So a little bit more involved example. So let's say that the category is dB of n-dimensional smooth projective variety. And then what the calculation produces is, sorry, I apologize. So f is the self functor. Then ht of S is equal to n dimension n times t plus c. So, and if x is fractional Calabi-Yau, then, in other words, the self functor in power m is equal to a shift by n, then this is just n over n times t. So I have prepared other examples, but I have only 4 minutes for the application, so I'll move on in this direction. So recall that the pseudo-Nosov transformations were the ones that were fixing certain points on the compactification of the Teichmüller space. And so if you study their classical entropy, they act as e in power lambda t or e in power minus lambda t. So by analogy with this, so let's say that X is symplectic, and the category that we consider is a Fukaya category. So we'll introduce a functor to be a pseudo-Nosov functor if and only if the entropy of it is equal to a constant. So, question. So, is it true that one can associate two transversal Lagrangian foliations with pseudo-Nosov functor f? So by analogy with the pseudo-Nosovs that act on Riemann surfaces, you have two Lagrangian, transversal Lagrangian foliations on these Riemann surfaces. Can you do this for every symplectic manifold as soon as you have a pseudo-Nosov functor in the Fukaya category? And being an algebraic geometer, I will try to talk about some applications to algebraic geometry. Just 2 minutes, please. So this is connected with so-called Cremona 2, group of birational automorphisms of P2. The non-simplicity of this group was recently announced, but it's not so well accepted to the East. So let's consider the following category. dBFX, X smooth projective. And we consider the following category, U of dBFX, defined by Usnich, in the following form. So I take the left orthogonal to the structure sheaf. So this means the full subcategory generated by left orthogonal to the structure sheaf, and then I mod out by complexes with support in codimension 2. All right, so let's just state it as a question. So does entropy of U dBFX determine by rational type of X? So I'll stop here.
One quick question.
So is H supposed to measure the number of limiting objects in the dense?
It is connected. It is connected, yeah. So
Can you say what it is for S9A1 or S7?
yeah, for all quivers I can give you a description.